So we're going to be doing another practice problem for the midterm. This one is number 10. The directions are to provide a mechanism for the following reaction. So you're given two starting materials, the reagent, and the final product. And your job is to provide the arrow pushing the intermediates that will show you how you got to the product. So the first goal is to figure out what type of reaction this is. Hopefully you've studied enough that you should know that this is going to be equation condensation. There's two reasons why that might be, three actually. First one is that your starting material has one ester in it. The second one is that your reagents, your first step is a base and your second step is a workup, which also relates with equation. And your third step is you form a 1,3 dicarbonyl compound. And if you remember, all your equation condensations will result in a 1,3 dicarbonyl compound, so it fits the profile for equation condensation. So again, first is determining which one is your electrophile and which one is your nucleophile. In the case of equation condensation, the compound that has the ester will behave as the electrophile. And so because this compound has the ester, it by default becomes the electrophile. And the reasoning for that is very briefly is that it contains a good leaving group. And so when we actually see the reaction occur, relative to the aldol reaction, where we actually have the O picking up an H, because of its negative charge, the O here drops down its electrons, reforming a carbonyl and letting this leaving group go. And so it's important to always have the electrophile as an ester so you can allow that to happen. Our ketone is going to be the other compound, and so that's going to be our nucleophile. And so using that, we'll go ahead and do the reaction. So the first step is a base. In this case, we're using methoxide. And that guy is going to pick up an acidic hydrogen at the alpha position, moving the electrons between the carbonyl carbon and the alpha carbon, and putting those electrons onto oxygen, resulting in an enolate. So we'll draw that out real quick. And so now you have your nucleophile. Forgot these double ones. Now you have your nucleophile, which is ready to attack the electrophile. Electrons in the O will drop down, and the electrons between the carbonyl carbon and the alpha carbon will go in and hit the carbonyl carbon of the ester, pushing these electrons onto oxygen. And so what our intermediate will look like is going to be, again, I like indicating which is the carbonyl compound on the second to make sure I'm getting all my substituents right. And so in this case, this guy is our second. He's connected to an ester as well as a 1,2 carbon chain as well as an O minus. Okay. Like I said before, because we're dealing with equation and not aldol, these electrons do not pick up a hydrogen, but instead they pick up, or they drop down to reform a carbonyl, and our leaving group comes off. So if we draw our second intermediate, so this guy is this carbon right here, reforms a C double bonded O, which is this. The ester comes off, which I'll draw right here, and it's also attached to a 2 carbon chain, which is that one right there. So we're almost done. Because we have a 1,3 dicarbonyl and because we have a base in solution, hopefully your malonic or acetoester synthesis reminds you that there's hydrogens here which are very acidic, and the acidity is because of the resonance that is provided by the adjacent carbonyls. And so because of the way the pKa's work out, the hydrogen will get deprotonated by this base, resulting in another enolate formation. So what you end up with, oops, didn't draw the enolate, fix that real quick. Is this compound right here. And so that's where our second step comes into place as a workup. And so the second step is H3O+. And so what happens is our enolate picks up one of those protons, from the solution and restores back to our final product. So you might be wondering, we already created our final product here. Why did we do this step? Unfortunately, how the reaction works out is the methoxide that's present here is always going to be in solution whenever this product is created. And so the acidic hydrogens that are planked by the carbonyls, one of the hydrogens will always be removed regardless if you want it removed or not. And so the only way to fix that is to do a second workup where we do our H3O+, and that restores it back to our normal state. So to recap, our ester is always going to be our electrophile because it has the good leaving group. The other compound is going to be our nucleophile. A base in this case it's methoxide, will come in, deprotonate at the alpha position, and result in an enolate structure. Our enolate is now able to act as a nucleophile, and it attacks our electrophile, which is our ester. We end up with an intermediate where we have O-, the ester, and the chain that's combined from their electrophile as well as our compounds from the nucleophile. Because of the good leaving group, the oxygen drops its lone pairs down, kicks off the leaving group, and we result in this 1,3-dicarbonyl, which is exactly what our product looks like. But it's very important that we show this step because when we kicked off the leaving group, in this case OCH3-, it's a good base, and a good base will always deprotonate acidic hydrogens. And so there's two hydrogens in this case that are planked between the 1,3-dicarbonyl. And one of those hydrogens will be removed, and so through our second step of working up, we're able to restore it back to its neutral state.